Okay, can you see my screen? Thank you very much.
No?
No. Okay, sorry. Let me do some setting. There seems some problem on my
Maybe you have just to change the view that you exchange the screens or something like that in Zoom.
yeah, my
You see, you see a black area that indicates that there is a presentation, but it's just the wrong monitor, which is somehow
yeah, my laptop here. Maybe I log out and later log.
You have not the option to exchange screen in Zoom. I think there's this option, change the screen or something like that.
Yeah.
Sorry. I'm sorry if you choose your PowerPoint to share or you share another.
Yeah, there's some problem on my Zoom. It has here, so I have to log out and log in again. Very sorry for this problem.
Okay.
Yeah.
Can you see my screen now?
Now we see
Yes.
something. So wonderful. Okay.
Okay. Sorry for this problem, and thanks, Professor, for your kind introduction, and also thanks for Professor Qianhong, Ho, and all the organization committees for inviting me for this talk. And it's very unfortunate that I'm not able to come to Taipei to attend this conference in person due to some reasons. I hope in the future we have a chance to meet in person. So today I'm going to share our research about the development of the electrochemically assisted membrane technology for energy efficient and low chemical desalination. Here, I actually want to focus more on the low chemical for desalination. I'm Qianhong from Nanyang Technological University. I'm working in the Singapore Membrane Technology Center. So this is the outline of my talk. I will first introduce the background of my research, and later I will introduce the development of different configurations of the electrochemical assisted membrane system. Firstly, I would like to introduce one of the most important chemical parameters. This parameter is pH. pH is very important. It is important for all the systems, for the life system, for the natural system, and also engineering system. In the engineering system, a membrane-based system is very important. It has been widely used in seawater desalination, wastewater reclamation, or separation of specific ions, and also resource recovery. And in the membrane-based treatment process, there is not only membrane, but also pretreatment, such as precipitation, coagulation, flocculation, and also membrane separation, and also the post-treatment. So all of these processes, actually, we need to think about the pH. pH plays a very important role to determine the treatment efficiency and also the membrane performance, such as the folding, scaling. So here I will specifically introduce the seawater desalination, because this is one of the most important areas for using membranes. And we know that seawater ion membranes, reverse osmosis membranes, can reject nearly all the solids or the salts in the seawater. However, the ion membranes cannot sufficiently reject boron. Boron is actually an important element in seawater, and the WHO stipulated that the boron concentration in the irrigation water should be lower than 0.5 ppm. And in most of the seawater desalination plants, they have a regulation. If they want to design a new plant, the product water after desalination should also reach this level below 0.5 ppm. And actually, we want in the seawater, the average boron concentration is about 5 ppm. And if you want to achieve the target to realize the boron concentration below 0.5 ppm, you have to reach a rejection above 90% for your outer membrane. However, this is a very difficult. What's the reasons? This is a question. And if we further look at the water chemistry of the seawater, so I think you know the pH of the seawater. The pH of the seawater is actually in the range of 8 to 8.2. And in this range, if we look at the boron species distribution, so in this range, so the majority of the boron exists in the form of the boric acid. And you can say boric acid has this kind of structure. It's very similar to water, and it is neutrally charged, and it has very small size. So that's why the reverse osmosis membrane cannot sufficiently reject the boron. And in the seawater desalination plant, therefore we have to consider boron removal. So if the seawater desalination plants want to remove the boron, most of the plants will consider to install another pass of the RO, not only the seawater reverse osmosis, but also the second pass RO to further treat the permit from the first pass RO. The major purpose is to remove the boron. And for the second pass RO, normally we use relatively loose outer membrane, brackish outer membrane, BWR membrane, and the energy consumption is 0.5 kilowatt-hour per meter cube water. And you know, the BWR membrane is relatively loose, although it can remove a certain amount of the boron, it still cannot sufficiently remove the boron. So in most of the case, in the seawater desalination plant, we will add alkalis to adjust the pH, to increase the pH, to enhance the boron removal. For example, if you look at this data, when the pH is low or near the neutral condition, the membrane rejection is only above 70%. If we increase the pH, then the boron rejection can be gradually increased. If the pH is above 10 or 11, the rejection can reach above 90%. And in the seawater desalination plant, not only the second pass RO will need to use chemical, but in the pretreatment, chemicals are also dosed to enhance the treatment efficiency and to remove, to reduce or mitigate the folding or scaling on the SWR membrane. So as we said, pH is very important. So currently, how do we adjust the pH? I think the direct way is to dose the chemicals, dose acid or base into the water to adjust the pH. In industry, in practice, the seawater desalination plants or wastewater treatment plants, they will first purchase very high concentration chemicals. For example, the caustic soda, the commercial chemical is at a concentration of 40%, and for acid also at a very high concentration, sometimes above 10 mole per liter. Or in this case, it will not only increase the cost for chemical consumption, but this cost is also related to the transportation and the storage of chemicals. And for storing this high concentration hazardous chemical, there is safety issues from the leakage. So this also increase some risks also, when we are using the chemicals in practice, we actually dilute the very high concentration chemicals to a very low concentration. In this case, there's actually irreversible energy loss because you in this dilution process, there's entropy generation. If we look at this process from the life cycle point of view, there will be energy loss. And if we further look at the chemical production, so for the caustic soda, for example, it is produced mostly from the chloralkali process. That means we use the electrochemical system to electrolyze the high concentration of the sodium chloride. Then in the cathode, there's a production of the sodium hydroxide. And this concentration is very high after the chloralkali. But if you want to produce a very highly concentrated caustic soda, sometimes people will further do the concentration using the thermal evaporation process. This also increase the energy consumption for the chemical production. Again, if we look at this chemical producing process, it is actually based on the electrochemical process. So inspired by this, we try to develop, we are thinking if we can integrate this electrochemical process together with the membrane separation to achieve efficient membrane treatment efficiency. So firstly, we design a system integrating the electrochemical process together with membrane separation. So in this system, we call the electrochemically assisted reverse osmosis, EARO. And in this system, we introduce external cathode. This external cathode is a carbon close, porous carbon close, that can simulate a kind of a feed spacer. And we place this carbon close on the surface of our membrane to simulate the spacer in a module. And we pair another anode in the system. And we design this system, and we want to evaluate whether this process is effective to help us to achieve sufficient remove efficiency for the boron specifically. And we actually want to make use of the electrochemical reaction to elevate the pH just from here in the cathode. So we actually want to use this process to elevate the local pH on the membrane surface. And then we want to evaluate whether the boron rejection can be achieved and what will be the salt transport and the water flux, whether they can be maintained stable. So we do the experiments, we apply the voltage in the system. So we just look at here, when there's a low voltage applied, the SWR membrane has a very low rejection to boron, just below 75%. So when we gradually increase the applied voltage from 1 volt to 2, 3, and 4, and the boron rejection gradually increase. And when the voltage is at 4, the rejection is above 90%. That means this meet our target. Our permit boron concentration is lower than 0.5 ppm. And meanwhile, you can observe that in the permit, when the voltage applied voltage in the electrochemical system increase, the permit pH also gradually increase. This suggests there's a hydroxide ion produced in the feed side that will also transport through the membrane and increase the permit pH. And here, look at the salt rejection and also the water flux. It is relatively stable during the operation under different voltage. So this means that if we integrate the electrochemical system together with our desalination process, the desalination efficiency and will be maintained. And meanwhile, we can improve the boron rejection. So as I mentioned just now, this is because the increase of the local pH on the membrane surface. So the question is that what will be the pH at different voltage? in a system, in a module system, you cannot use a pH meter to directly measure the pH on the local memory surface. So in this case, we actually want to understand the pH, the relationship between the voltage and the pH. So we design some experiments to indirectly measure the pH. So we first look at this ion transport profile. The ion membrane, although the hydroxide ion is very small, but the ion membrane still can reject certain amount of the hydroxide ion. So in the permeate side, the hydroxide ion concentration will reduce. So if we directly measure the permeate pH, this cannot reflect the actual local pH on the feed side. In this case, we use another membrane, UF membrane, to replace the ion membrane. And in this case, the UF membrane cannot reject the salt ions, especially the hydroxide ion. So in this case, we just measure the permeate pH, and this permeate pH can indirectly indicate the local pH on the memory surface, approximately. So in this case, we measure the different permeate pH using the UF membrane in the electrochemical UF process. And we can find the at different voltage, there's a different pH. And before that, we do some calibration. So you can see there's a very good correlation between the feed pH and the permeate pH. So this means that when the voltage at a certain voltage, the pH measured in the permeate side can indicate local pH on the memory surface. So in this case, we can find that if the applied voltage is about 4, the local pH is actually around 10. So that's why if the feed pH increase to about 10, the boron rejection can be improved, because at a higher pH, the boron species change from the boric acid to borate ions that has a larger size and that is negatively charged. The ion membrane can readily reject the boron. Of course, we want to lower the energy consumption. This is important for for the electrochemical system. And ideally, if we assume the efficiency, the electrochemical reaction efficiency is 100%, there's a low energy loss. All the electron transfer is used to produce it's used sufficiently used in the redox reaction and produce the hydrogen or hydroxide ions. The energy consumption will be very low if our target is to elevate the pH above 10. So at different voltage, the theoretical energy consumption will be very low, even lower than 0.001. But in reality, we measured the energy consumption. It's a little bit high. You can see it's about 5 kWh per meter cube. And if we want to use this method to enhance boron removal and to eliminate the second pass RO, our target energy consumption should be lower than 0.5 kWh per meter cube. So this is our target. It means that we need to further optimize the module design. And actually, if we further look at this system, there's actually some problem. We have to admit, in the feed side, why the energy consumption is very high? Because the applied electric potential is not sufficiently used to elevate the pH. In this system, the cathodic stream and the anodic stream is on the same side of the membrane. And in the electrochemical reaction, there's actually the mixing between the cathodic stream and anodic stream. Due to the mixing, the hydroxide ion will be consumed by the products from the produced in the anodic stream. So in this case, the pH will not be sufficiently elevated. You have to apply a very high voltage to elevate the surface, the local pH. This will increase the energy consumption. So the question is that, can we further improve the design. So in this case, we design another system. We just use a membrane to separate the cathodic stream and anode stream. So in this case, this membrane actually acts as a barrier to separate these two streams. And of course, this membrane, we just use this membrane. This membrane is a kind of a filtration membrane. So for the filtration membrane, you can also do the filtration. You can integrate the membrane filtration with the electrochemical reaction. So this is actually a kind of a flow through electrochemical membrane system. And you can operate this in the non-filtration mode or in the filtration mode. And potentially, you can achieve the change of the pH. So we try to evaluate the performance of this system. And we use active carbon as electrodes just coated on the titanium plates. And we tested different feed solution, such as 2 millimole sodium chloride that represents with water or tap water, and also tested higher salt concentration or synthetic seawater, and under the voltage of 1.2 volts. And we found that we first test the baseline conditions. So for this design, this configuration, there's a low membrane inserted. So in this case, you can see this configuration is very similar to conventional CDI cell, right? So in this case, we measure the effluent pH. Although initially there's some change of the pH, but at the effluent, the pH gradually decreased to the same level to the influent pH. Again, this is because there's actually a mixing between the cathode stream and anode stream. So the pH actually is neutralized, even there's a production of the hydroxide or hydrogen ions. And this is actually, I just want to say initially, we want to do the CDI, we tested this, but later we found that the pH change is more interesting. So we focus more on the pH study. So in this case, we tested the electrochemical membrane system. We insert a filtration membrane here, and we can see that in the anodic stream or cathodic stream, there's a change of the pH. In the cathode side, the pH is elevated above 10, and in the anode side, the pH is decreased to below 4 or even lower, depending on the operating conditions. And we also tested the filtration mode. During the filtration mode, so you can actually put the cathode either in the permeate side or in the feed side. So in this case, there's a change of the pH in both feed side and permeate side. And we can effectively achieve the adjustment of the pH in this electrochemical system when we use the membrane to separate the two streams in the electrochemical system. And we also tested the pH change under different voltage. So when we increase the voltage, the pH change would be more significant. And this actually suggests that we can manipulate the voltage to adjust the pH to our desired level. And we want to understand the reason for this change. So we further look at the electrochemical reactions on cathode and anode. So in the anode, there's actually oxidation reaction, and this reaction, different reactions will occur under different voltage, different potential, electric potential. So for example, there will be the chlorine production. There will also be the oxidation of the carbon if we use the active carbon as electrode. And these chemicals, this reaction, all of this reaction actually will produce hydrogen ion that will lead to the decrease of the pH. And for some chemicals, we actually can make use of. For example, the chlorine is actually a disinfectant. If we can properly design the system, we can make use of the chemicals produced in the anode. Similarly, in the cathode, there's a reduction reaction. There's a production of the hydroxide ion that can increase the pH. Under different voltage, there will be different reactions. So we also want to understand why, when we put the membrane here, we can achieve the control of the pH. So in this case, we want to analyze the ion transport, and we can do a simple mass balance and try to understand what factors will influence the ion transport. So if we select the hydrogen ion or hydroxide ion as our target ion to analyze its transport, from this analysis, we can see that, for example, if we use hydroxide ion to do the analysis, so the hydroxide ion production is related to the electrochemical reaction that is here, and it will also transport through the membrane from the cathode to the anode. Its transport is related to different factors due to the concentration difference diffusion or electrochemical electric potential difference due to the electromigration, and also due to the water transport if there's a water flux through the membrane due to the convection. And this will influence the ion transport. And eventually, some other factors in this transport, the membrane property also play a very important role that will influence the diffusivity here. So the membrane structure can influence the ion transport, can also influence the pH change. And a lot of factors related to the surface loading rate, that means the flow rate over the electrode area. So this will also influence the pH change, a higher level, a lower change of the pH. So another factor we want to evaluate is the energy consumption. So in this system, you can see if we want to change the pH to above 10, for example, in the cathode side, the applied voltage can be very low, only at 0.6 volts. And the energy consumption will be very low, just lower than 0.005 kilowatt hour per meter cube. So this demonstrates that this system can achieve very low energy consumption. So now the question is that how can we use this system in practice? So we design another process. We say this is a flow-through electrochemically assisted our process. We introduce the anode feed spacer and also the cathode permeate carrier. So in this case, we can make a module in our system, integrate the electrochemical system with the SWR desalination process. And in this case, we can achieve the elevation of the pH in the permeate side, and this elevated pH permeate can be directly fed into the second pass hour for boron removal. And in the feed side, there's a production of the chlorine. So depending on the operating condition, again, we can manipulate the chlorine production concentration, and then we can achieve the use of this chemical to mitigate the folding or scaling. And in this process, if we look at the energy consumption, it's very, very low, less than 0.005 kilowatt hour per meter cube. And eventually, we can, based on this concept, to design a module integrate into the first pass hour, and eventually we can achieve almost chemical-free for this desalination process. And in the second pass hour, you can say you don't need to add caustic soda. In the first pass hour permit already has an alkaline condition, so it can realize the rejection of the boron to the target concentration. So to conclude, we designed different electrochemical membrane system, and different systems have different advantages and also disadvantages. And very importantly, in the future research, we hope we want to optimize the module design. Actually, this is our current ongoing work to scale up this system in a spiral wood module. And a question here is that which system is really useful in practice that can be scaled up for real applications. I'm talking about the electrochemical membrane system. So this question is for us to think about. Finally, I would like to thank the funding agency and also my students to work on this project. Thank you.
Thank you, Professor Xu, for your nice presentation. And we have a little bit time constraints, but maybe we can take one quick question from the audience here, if I see. Otherwise, there have been popped up some, you see the questions, right?
Let me check.
The chat, yeah, there should be. So maybe you can choose one or two questions and then we...
The first question, could you introduce how to measure the local pH in the membrane surface in detail? Just now we mentioned that we just changed the R membrane into the UF membrane just to indirectly measure the pH. And if you want to know more, you can read our paper published in JMS. I can share the paper with you.
Mm-hmm.
And the same question, the results shows the increase in pH and the voltage increases. However, the study has been investigated up to 4 volts. What happened when tested above 4 volts? It seems it's not equilibrium voltage. As we mentioned, at the high voltage, there is a higher change of the pH. But actually, for the first system, flow by EAR system, we do not think it is really promising. We just do that research, just want to demonstrate the concept. But for real applications, maybe my opinion is that we should consider the flow-through system. And also the voltage at 4 is very high, and there will be many other reactions. So that is also not good for the electrochemical system, not good for the electrodes or membranes, even for, What's the property of the filtration membrane in EMS? So for the filtration membrane, you can use whatever membrane. You can use UF, MF, or RO membrane. If you look at our results, we have tested all the membranes, especially for the R membrane, for the SWR membrane. I think we are the first to test the SWR membrane in this kind of system, and we demonstrate its feasibility to use SWR membrane in the electrochemical system.
Mm.
Is there any relationship between pH and the energy consumption? Yes, we have shown here, but let me see. So here just shows the relationship between the pH change and the energy consumption. In general, overall, the energy consumption is very low, although we can elevate the permit pH to above 10 to the desired level for achieve boron removal efficiency. So I think I have answered all the questions here in the chat. I'm not sure if there's any questions from the audience.
Well, I don't see any further questions. So then thank you very much again for your nice presentation, and have a still, a good day in Singapore.
Thank you very much. Hope to see you in the future in person. Thank you. Yeah.